Okay, it's my pleasure to pivot to the next talk in today's session. That'll be given by Professor Sharon D. Sharon D is an assistant professor in the Department of Civil Engineering and Engineering Mechanics at Columbia University. And she's been working on this really interesting intersection of game theory, dynamic control, data science, and transportation engineering, kind of linking the full spectrum of theory into practical applications. Before Sharon joined Columbia University, she was a postdoctoral researcher at the University of Michigan, where she worked at UMTRI, and she earned her PhD at the University of Minnesota. Sharon has won a number of awards, including a Best Paper Award, winning a data science competition at TRB, but most recently, she was selected for winning the National Science Foundation Career Award. So really important milestone, and we're excited that she has earned that distinction. So Sharon's going to be talking today about physics-informed deep learning for traffic state estimation. Sharon's going to be joining us at the start of the talk by video, but then she is online and will be available to answer questions for us after the talk. So we'll give Sharon the floor, and Amaury, if you wouldn't mind playing the video, we'll get it started. Thank you.
At Columbia University, and today I want to talk about our ongoing work using physics-informed deep learning for traffic state estimation and the discovery of fundamental diagram. This is a joint work with my PhD student and postdoc, as well as my collaborators from applied math. Traffic state estimation is an old problem. Basically, traffic engineers aim to infer the spatial temporal evolution of traffic states using data collected from sensors. So the states can be represented by traffic density, speed, and volume. And the sensors include conventional loop detectors, probe vehicles, and overhead cameras. The most widely used method is the model-based. So that assumes all these data are generated from some underlying equations. And then the data are used to calibrate the parameters inside the model, such as the first or second order traffic flow model. Recent years, we are seeing a growing trend using machine learning methods, in particular deep learning, to directly discover the pattern from the data. However, training deep neural networks requires a large number of representative samples, but that's not the case for traffic state estimation. Usually we have a small data set. How can we train neural networks using these sparse sensors is a question we want to answer for this research. And we found out that, okay, since the neural networks can discover patterns that are hidden in data that may not be able to capture by existing domain knowledge, but on the other hand, the traffic flow model can also provide physical constraints to the neural networks so that they can narrow down search space during the training process. That's why in this study, we suggest to combine these two frameworks and develop a neural network regularized by traffic models. And we found out that it outperformed both model-based and data-driven methods, especially under the small data region. We will demonstrate our finding using data generated from LWR model and also on real-world data set, NGCM. This study is motivated by a testbed that is deployed near Columbia campus for Internet of Things. So this testbed is called Cosmos. And this Cosmos testbed aims to validate the emerging communication technology, including Wi-Fi, 5G, and beyond in an urban setting. This is a map of where these communication nodes are deployed. It actually covers from Columbia campus all the way up to the campus of City College of New York. This is a broad way you can see that connect these two campuses, and then there are several infrastructure on the side of the road mounted with communication nodes and also overhead cameras. The research question here is, with all this data collected from IoT, whether we can leverage them to better understand how we can infer traffic as traffic states real time. Let me first show you a graph comparing the physics-based versus data-driven methods. So the x-axis represents the amount of the data used for each model, and the y-axis represents the amount of domain knowledge it requires to train a model. So physics-based model, we call the model-based approach or theory-guided approach, usually focus on the left-hand quadrant. So that means the physics-based model use very little data, very small amount of data, but they highly rely on people's domain knowledge and the scientific hypothesis. Machine learning models, in contrast, you highly rely on the data with little or no prior knowledge about the domain or how physics actually works. To combine them, we try to use emerging framework called physics-informed machine learning, or PIML for short. So for this framework, it leverages the benefits of both physics-based and machine learning models, which is, it requires only a small amount of data to train neural network, but can achieve a higher accuracy compared to both physics-based or data-driven models. And the PIML has seen a growing trend in various science and engineering fields, such as earth science, fluid dynamics, and neuroscience. However, its application to transportation is still remain understudied. Let me first frame how we apply PIML for transportation application in traffic state estimation. This is a partial differential equation. So rho represents the solution of a physical value of interest, such as the density, traffic density or traffic velocity field. And n of x is a nonlinear differential operator, and it's calculated using the derivative with respect to x. And the t and x are represent the time and space domain. And the goal of this PIML is to train a neural network that can approximate the solution of the original partial differential equation. How it works? So we can represent this neural network as n of theta. And the input of this neural network is t and x pair, which represents the time and the space domain. And output is rho. If this neural network can approximate the solution of the original partial differential equation, then we can substitute this rho value into a R function, and we call it residual. And if it accurately measures the original solution, then this residual should equal to 0. So then we can replace, we don't have to actually numerically solve partial differential equation anymore. Instead, we can just train this neural network. And then whenever we input one pair, the neural network would tell us what the value of rho is at the t and x. But how we train this neural network? So let me talk about the flow chart of this training process. So the neural network N of theta is our target. And we have some observation at a certain time and certain time t and certain location x. So if this neural network is already trained, then it can output some value rho. And we also have observed the rho at those time t and x location. Then we can calculate the distance between these two values. That gives us a mean square error defined over the observation set. On the other hand, we can define a set of co-location points. So they also include a set of tx paired. And then when it's fed into the neural network, it also gives a predicted value of rho for each tx pair. However, we don't have observation on those tx pairs. Instead, we can feed this rho into a physics model. For example, here I use LWR as an example. In the equation U of rho represents the fundamental diagram we will use that define the mapping from rho to a velocity U. And then we feed rho into this LWR model by calculating its partial derivative with respect to t and x. Then we can get a residual that is defined in the previous slide. Then we can calculate a weighted sum based on the mean square error and also the residual. We achieve a loss function. This loss function will be used to train the neural network. If the loss function is achieved at its minimum, then we know that this training process is done. The neural network we obtain is already the optimal one. If it's not, then we will update the hyperparameter theta contained in the neural network. Meanwhile, we have to also update the parameters that are used in the LWR model. Okay, this is the whole training process. And by the end of this training, we will get an optimal neural network. And the solution, the output of this neural network should approximate the solution of the original physics model. This is the idea, and I will demonstrate how this works using LWR as the physics. And you can see the upper part, those blue arrows represents the data-driven approach. And lower part, the red arrows represents how this physics-based flow is used. And then we integrate them to as one loss function. So you can treat this loss function as basically original loss function for neural network, but regularized by the physics. Okay, so now let's give you an example to demonstrate that process. We just use an ideal LWR model. The first equation is a flow conservation. The second is the fundamental diagram. We use the green shield here. And the domain x and t are defined. We also define initial condition and boundary condition. So we assume it's a ring road. That's why the density at the starting point and ending point are the same. And then we can theoretically solve this LWR system using numerical methods, and I provided the numerical solution here in the t and x domain. However, if we have some observations, these observation data we call it label data because it contains both the tx pair and their target value rho. So these observations can be measured, say, on the initial condition. So at time t, assume we know all the traffic density along this road. And we know also the boundary conditions. For example, we place the two loop detectors at the starting point and ending point. And if there are some also loop detectors within the domain, we can also measure the density rho in those fixed locations across time. Or we have another type of sensor like mobile probe vehicles. Then we basically the density near the trajectory where this car is passing by can be measured. So this is the observation data we have. And also let's introduce collocation data. We call it unlabeled data because we only select a TX pair. We don't know its target value rho. The rho will be calculated by the physics model we want to incorporate in the framework. So here, I assume we randomly select some TX pair from this domain. That is represent, each point is represented by a black cross. So then we assume we have some observation data here. The red bars represent where the loop detectors are located. That's why we only collect the data for those fixed locations across time. And then we also have collocation points pre-selected. Then only based on these data, we can actually train a neural network following the step I introduced in the previous slide. And based on this loss function. And the MSE is to measure the distance between the predicted rho from the observed rho. And this R residual measures the distance of how this predicted rho far from the computed rho using the physics. And the observation data can come from initial condition, boundary condition, or any data points within the domain. So using this weighted loss, then we train the neural network, and then this is the result we get. So we can reconstruct the spatial temporal traffic density field using those sparse data. Okay, so this example demonstrates how this PIML works if we only have sparse measurements. Now we will move on to the real world data set, NGSIM. But before that, let me talk about how we improve upon the framework that we discussed before. So this is the same training process for the physics-informed machine learning we discussed. The only difference here is because when we run this LWR model physics-based component, we have to also know what fundamental diagram the data has. But in real world, we don't know exactly what's the mathematical mapping from the density rho to velocity u. That's why we replace it by another neural network we call the fundamental diagram learner, or FD learner for short. It's denoted as n of lambda, so it's a neural network parameterized by parameters lambda. And now this physics-based component is not the LWR model anymore, and we call it a machine learning surrogate model. So it follows the structure of LWR. Actually, it only uses the information of flow conservation. However, we use this neural network to approximate fundamental diagram. And then the training, when we update the lambda, so this lambda is not the model parameter involved in LWR anymore. It's also the hyperparameters used by the FD learner. And by the end of the day, so what we will end up is the trained neural network plus this FD learner. And we apply this framework to the real world NGSIM data. Here we use the US 101 data set. The original data was collected using the overhead cameras facing that highway stretch. And we can aggregate those vehicle trajectory data and generate a ground truth traffic density map for that T and X domain. So this heat map represents the ground truth. And now we will randomly select some data. For example, we place 3 sensors along this stretch evenly distributed, and then only measure the density for those fixed locations across the entire time. And we gradually increase the number of sensors. And then using only this sparse data, we reconstruct this density field using the previous method. And here's the result. And in this figure, the x-axis is the number of loop detectors. We gradually increase the loop detector. Basically, we increase the training data. And the y-axis is estimation error. And each line represents one model. And the blue one is just the pure neural network without using any physics. LSTM is the long short-term memory model. EKF is the classical method for traffic state estimation. Its full name is extended Kalman filter. And the PIDL, the physics-informed deep learning model, is the model we propose. And you can see this, the lowest curve is the performance of our model. It has a lower estimation error compared to other models, especially when you look at the small data regime when there are only 2 or 4 loop detectors. Our model outperforms all other models and have a much higher accuracy. However, when the training data size grows, all these models gradually converge. The reason is because this deep learning model will more and more rely on the data, and they can better and discover the pattern from the data. And the right-hand side is another figure. The x-axis is still the number of loop detectors, but the y-axis is the ratio of beta over alpha. So if I refresh your memory, alpha is the weight in front of observation discrepancy. Beta is the weight in front of physics discrepancy or residual. So this ratio represents how much the physics play a role in training a neural network. You can see as the number of training data grows, the role that physics plays also diminishes. However, when there are only 2 or 4 loop detectors, which means there are very sparse data, and the physics play a bigger role to train a better model. Now we apply fundamental diagram learner, or FDL for short, to the NGSIM data. Let's look at the left-hand side figure. The x-axis is the number of loop detectors, and the y-axis is the estimation error. And we tried 4 models. The blue one is the LWR with the FDL. So there's no mathematical formula of what the fundamental diagram look like. And we try to learn the mapping using another neural network. The purple is the LWR using the predefined 3-parameter green shows fundamental diagram. The orange is the ARZ with FDL, and the red is the ARZ with green shows fundamental diagram. First of all, we can clearly see that the models using FDL outperforms those without. Second, I want to draw your attention to these 2 lines, which is the LWR and ARZ plus FDL. So surprisingly, in the small data regime, LWR and FDL outperforms ARZ FDL. This is because ARZ is a more complex second-order model. It involves a lot more parameters to train and tune. So when there are only a few data points, the model tends to overfit. And in this case, LWR is easier to train and achieve better performance. Right-hand side is the fundamental diagram. And here we focus on only 3 loop detectors, which is small data regime. The background, those black points are generated from the real data. X-axis the density and Y-axis the traffic volume. Okay, this is the shape of the LWR FDL. So here we as I explained, there's no pre-knowledge of what a fundamental diagram look like. So we use a neural network to learn that shape. Then we can generate this curve. This is the standard 3-parameter green shows FD. And the orange dashed line is ARZ with FDL. And the red one, the ARZ with the standard green shows fundamental diagram. If you look at the capacity part, so LWR ARZ plus FDL can better capture the capacity part. And if you look at the congestion part, actually the LWR FDL can predict a much better congested density than the ARZ FDL. So that blue line, its intersection with the traffic density is around 0.7. That's the value that is reasonable and also consistent with the value we estimate directly from data. So based on these 2 figures, we can say that for NGSIM data, LWR FDL perform the best, especially in small data area. So that's all about my talk today. How we apply physics-informed deep learning for traffic state estimation. And also we present the joint estimation of fundamental diagram.
All right, thank you. Just a reminder for folks, we do have Sharon here live on the Zoom call, so I'd like to open the floor for questions if anyone has a question they'd like to ask Sharon.
So I may have a question. So thank you, Sharon, for the talk. It is not clear to me the final part where you learn the fundamental diagram. So what do you mean by learning the fundamental diagram?
So essentially, we are learning actually the mapping from the traffic density to velocity.
Okay.
Yeah, probably we abuse this concept, the term fundamental diagram.
So how do you explain that the result basically don't see all the upper part of the data set?
You mean like the capacity regime?
Yeah, all the data points that are,
those
close to the maximum,
so actually for both LWR ARZ plus FDL, so they are very pretty close in that area. So we didn't basically ignore all those like a capacity drop or anything in the data. So we just want to see whether we can capture that maximum value. So those 2 models are basically consistent quite well, but it's the jam density part, like they have some deviation. And we also only use the mean square error to evaluate these models.
Okay.
So we found out LWR plus fundamental diagram learner works better. Yeah, but if we really want to look into those physical phenomena, so we may need to come up with some other metrics.
Okay, thanks.
Okay, we'll maybe allow for one more question before we go to break, if there's another question from the audience. and I'm standing between everyone and their bio breaks and lunch breaks and everything else. So I'd encourage everybody to reach out to Sharon if you have additional questions or things you'd like to discuss with her about her presentation. Sharon, we're really grateful for you to join us today. Thanks for your great talk, and really appreciate the opportunity to hear about your work. So thank you all. We'll be regrouping here in about 12 minutes. So